Design a time-based key-value store. Set stores a key, value, and timestamp. Get looks up a key at a query timestamp and returns the value whose stored timestamp is the largest one still less than or equal to that query. If nothing qualifies, return the empty string. For key foo, set bar at time 1. Get at time 1 reads bar directly. Get at time 3 still reads bar because 1 is the latest timestamp not after 3. Set bar 2 at time 4. Get at time 4 returns bar 2. Get at time 5 also returns bar 2. Example 2, set val on key at time 10. Get at time 5 finds no timestamp at or before 5, so the answer is empty. Get at time 10 hits the stored pair exactly and returns val. We organize our store using a standard hash map where each unique key maps to a dynamic array timeline. Because incoming snapshots arrive with strictly increasing timestamps, our timeline array is naturally presorted from left to right. When fetching data, we locate the key's history and sweep across the array. If the requested timestamp matches an existing entry exactly, we extract its value and return it immediately. When a timestamp is missing, we use binary search to partition the timeline against our target. Elements exceeding our target flash red as invalid future states, while elements below or equal to our target glow green as valid history, letting us instantly isolate the closest possible past snapshot. Our binary search must also catch the boundary floor. If our target timestamp sits entirely before the very first entry in our array, our search partitions everything into the future, revealing that no history exists and safely returning an empty string. We construct our solution using a global hash map. The key maps directly to a dynamic array of integer string pairs, allowing us to isolate each unique key's history onto its own standalone chronological timeline. The insertion operation remains incredibly lightweight. We locate or create the list bucket for the given key and append our time-stamped pair directly to the end of the array, preserving our sorted invariant effortlessly. When fetching a value, we run a binary search over the key's history array. Every time our midpoint timestamp is less than or equal to our target, we know we found a valid history state. We cache its value as our best answer so far and shift our search window forward to look for a more recent match. Finally, we resolve our output. If our binary search successfully trapped a historical candidate, we pass it back as our optimized result. Otherwise, if the target sat entirely before our timeline even began, we gracefully default and return an empty string. Let n be the number of snapshots stored for one key, and s the total pairs stored across all keys. Set is constant average time, hash map lookup plus append to the end of a presorted list. Get is order log n, binary search on that key's timeline for the largest timestamp still at or before the query. Space is order s for the map and all timeline lists combined. Timemap maps each key to a sorted list of timestamp value pairs. Set appends a new pair to that key's timeline. Get binary searches for the best past snapshot at or before the query timestamp, and returns the empty string when no history qualifies.